career. Most notably, in 2018, he received the Turing Award, what we call the Nobel Prize in computer science. Today, Professor Lacombe will give a speech entitled Toward the Machines That Can Learn, Reason, and Plan. Let's welcome Professor Lacombe. Yang, the floor is yours. Thank you.
All right. Thank you very much for the introduction. I hope you can hear me fine. I'm really sorry I can't be there in person. Haven't been to China in a very long time. So I'm going to talk a little bit about the future of AI, the way I see it, and to essentially bridge the gap between what we observe in the capacity of humans and animals and the type of artificial intelligence we're capable of producing today. And what's missing is the capacity to not just learn, but also reason and plan in AI systems. So a lot of what I'm going to talk about is either kind of a direction, if you want, where I think AI research should go in the next decade or so, as well as some preliminary results, but no complete systems. So the first thing I should say in sort of colloquial English is that machine learning is not particularly good compared to humans and animals. For a few decades now, we've been using supervised learning, which requires too many labels. Reinforcement learning works well, but requires an insane amount of trials to learn anything. And of course, in recent years, we've been using a lot of self-supervised learning. But the result is that those systems are somewhat specialized and brittle. They make stupid mistakes. They don't really reason nor plan. They sort of react really quickly. And when we compare with animals and humans, animals and humans can learn new tasks extremely quickly and understand how the world works and can reason and plan. And they have some level of common sense that machines still don't have. And that's a problem that was identified in the early days of AI. That's partly due to the fact that current machine learning systems have essentially a constant number of computational steps between input and output. That's why they really can't reason and plan to the same extent as humans and some animals. So how do we get machines to understand how the world works and predict the consequences of their actions like animals and humans can do, can perform chains of reasoning with unlimited number of steps, or can plan complex tasks by decomposing them into sequences of subtasks? That's the question I'm going to ask. But before I say this, I'll talk a bit about self-supervised learning and the fact that it really has taken over the world of machine learning over the last several years. This I've been advocating for quite a number of years, 7 or 8, and it's really happened. A lot of the results and the successes of machine learning that we see today are due to self-supervised learning, particularly in the context of natural language processing and text understanding and generation. So what is self-supervised learning? Self-supervised learning is the idea of capturing dependencies in an input. So we're not trying to map an input to an output. We're just being provided with an input. And in the most common paradigm, we mask a part of the input and we feed it to a machine learning system. And then we reveal the rest of the input and then train the system to capture the dependency between the part that we see and the part that we don't yet see. Sometimes it is done by predicting the part that is missing, and sometimes not entirely predicting, and that's well explained in a few minutes. So that's the idea of self-supervised learning. It's called self-supervised because we essentially use supervised learning methods, but we apply them to the input itself as opposed to kind of mapping to a separate output that is provided by humans. So the example I show here is a video prediction where you show a short segment of video to a system and then you train it to predict what's going to happen next in the video. But it's not just predicting the future, it could be predicting kind of data in the middle. So this type of method has been astonishingly successful in the context of natural language processing, and all the success that we've seen recently in large language models are a version of this idea, right? So the basic principle here is that you take an input, a text, let's say a window over a piece of text, and by removing some of the words, replacing them by a blank marker. And then you system runs a represent text, and the astonishing thing is that it can do this which is for a subsequent task. My apology, it turns out my computer has a hardware problem and just crashed. So I had to reboot. I hope this is going to take us to the end. Okay, so I was saying this self-supervised learning technique consists in taking a piece of text, removing some of the words in that text, and then training a very large neural net to predict the words that are missing. And in the process of doing so, the neural net learns a good internal representation that can be used for a number of subsequent supervised tasks like translation or text classification or things of that type. So that's been incredibly successful. And what's been successful also is generative AI systems for producing images, videos, or text. And in the case of text, those systems are autoregressive. So the way they're trained using self-supervised learning is by not predicting random missing words, but by predicting only the last word, right? So you take a sequence of words, suppress the last word, and then train a system to predict the last word, the last token. They're not necessarily words, but subword units. And once the system has been trained on enormous amounts of data, you can use what's called autoregressive prediction, which consists in predicting the next token, then shifting that token into the input, and then predicting the next token, and then shifting that into the input, and then repeating the process. So that's autoregressive LLMs, and this is what the popular models that we've seen over the last few months or years do. Some of them from my colleagues at Meta, at FAIR, Blunderbot, Galactica, and Llama, which is open source. Alpaca from Stanford, which is a refinement on top of Llama. Lambda, Bard from Google, Chinchilla from DeepMind, and of course ChatGPT and GPT-4 from OpenAI. The performance of the systems is amazing if you train them on something like a trillion token or 2 trillion tokens. But in the end, they make very stupid mistakes. They make factual errors, logical errors, inconsistencies. They have limited reasoning abilities, produce toxic content, and they have no knowledge of the underlying reality because they are purely trained on text. And what that means is a large proportion of human knowledge is completely inaccessible to them. And they can't really plan their answer. There's a lot of studies about this. However, those systems are amazingly good for as writing aids, as well as for generating code, for helping programmers writing code. So you can ask them various things to write code in various languages, and it works pretty well. It gives you a good start. You can ask them to generate text, but again, they can hallucinate or confabulate stories. So this is a joke that my colleague played on me. They said, "Did you know that Yannick dropped a rap album last year? We listened to it, and here is what we thought." And the system comes up with some story that somehow I produced a rap album, which of course is not true. But if you ask it to do it, it will do it. So that's entertaining, certainly, but that makes the system not so good for as information retrieval systems or as search engines, or just if you just want factual information. So again, they're good for writing assistants, first draft generation, stylistic polishing, particularly if you're not a native speaker in the language that you're writing. They're not good for producing factual and consistent answers, taking into account recent information because they have to be retrained for that. They mimic behavior in the training set, and that is no guarantee that they will behave properly. And then there is issues like reasoning planning, doing arithmetics and things like this, for which they would use to have tools such as search engines calculator, database queries. So that's a really hot topic of research at the moment, of how to essentially get those systems to call tools. This is called extended language model. And I co-authored a review paper on this topic with some of my colleagues at FAIR on the various techniques that have been proposed for extended language models. We're easily fooled by their fluency into thinking that they are intelligent, but they really are not that intelligent. They're very good at retrieving memories approximately. But again, they don't have any understanding of how the world works. And then there is kind of a major flaw, which is due to the autoregressive generation. If we imagine that the set of all possible answers, so sequences of tokens, is a tree, if you want, here represented by a circle, but it's really a tree of all the possible sequences of tokens. Within this enormous tree, there's a small subtree that corresponds to the correct answers to the prompt that was given. And so if we imagine that there is an average probability E that any produced tokens takes us outside of that set of correct answers, and the errors that are produced are independent, then the probability that the answer of length n is correct is 1 minus e to the power n. And what that means is that there is an exponentially diverging process that will take us out of the tree of correct answers. And this is due to the autoregressive prediction process. There's no way to fix this other than making e as small as possible. And so we have to kind of redesign the system in such a way that it doesn't do that. And in fact, other people have pointed the limitations of some of those systems. So I co-wrote a paper, which is actually a philosophy paper with my colleague Jacob Browning, who is a philosopher, about the limits of training AI systems using language only. The fact that those systems have no experience of the physical world, and that makes them very limited. There's a number of papers either by cognitive scientists, such as the one on the left here from MIT group, that basically says, the kind of intelligence that the system has is very restricted compared to what we observe in humans and animals. And there are other papers by people who come from sort of more classical AI, if you want, sort of not machine learning based, that try to analyze the planning ability of those systems and basically conclude that those systems cannot really plan, at least not in ways that are similar to what people were doing with sort of more classical AI search and planning. So how is it that humans and animals can learn so quickly? And what we see is that babies learn an enormous amount of background knowledge about how the world works in the first few months of life. They learn very basic concepts like object permanence, the fact that the world is three-dimensional, the difference between animate and inanimate objects, the notion of stability, the learning of natural categories, and the learning of very basic things like gravity, the fact that when an object is not supported, it's going to fall. Babies learn this around the age of 9 months, according to this chart that was put together by my colleague Emmanuel Dupuy. So if you show a 5-month-old baby, the scenario here at the bottom left, where a little car is on a platform and you push the car off the platform and it appears to float in the air, 5-month-old baby are not surprised, but 10-month-old baby will be extremely surprised and look at the scene like the little girl at the bottom here, because in the meantime they've learned that objects are not supposed to stay in the air; they're supposed to fall under gravity. And so those basic concepts are learned in the first few months of life. And I think what we should reproduce with machines is this ability to learn how the world works by watching the world go by or experiencing the world. So how is it that any teenager can learn to drive a car in 20 hours of practice, And we still don't have completely reliable level 5 autonomous driving, at least not without having extensive engineering and mapping and LiDARs and all kinds of sensors, right? So obviously we're missing something big. How is it that we have systems that are fluent, that can, pass the law exams or medical exams, but we don't have domestic robots that can clear up the dinner table and fill up the dishwasher, right? This is something that any 10-year-old can learn in minutes. And we still don't have machines that can come anywhere close to doing this. So, we're obviously missing something extremely major in the AI systems that we currently have. We're nowhere near reaching human-level intelligence. So how are we going to do this? And in fact, I've kind of identified 3 major challenges for AI over the next few years: learning representations and predictive models of the world, of course, using self-supervised learning, learning to reason. So this corresponds to the idea from psychology, from Daniel Kahneman, for example, of system 2 versus system 1. So system 1 is the kind of human action or behavior that corresponds to sort of subconscious computation, things that you do without thinking about them. And then system 2 are things that you do deliberately, consciously. You use the full power of your mind. And current AI systems basically only do system 1 and not very good at all. And then the last thing is learning to plan complex action sequences hierarchically by sort of decomposing complex tasks into simpler ones. So I wrote a vision paper about a year ago that I put up on Open Review that you're invited to look at, which is basically my proposal for where I think AI research should go over the next 10 years. The title is A Path Towards Autonomous Machine Intelligence, and which is sort of a written version of the talk you're hearing right now, if you want. It's based around this idea that we can organize a variety of modules into what's called a cognitive architecture. And within this system I'm proposing, the centerpiece is the world model. So the world model is something that the system can use to basically imagine a scenario, imagine what's going to happen, perhaps as a consequence of its act. So the purpose of the entire system is to figure out a sequence of actions that, according to its own prediction using its world model, is going to minimize a series of costs. So the costs, you can think of them as measuring the level of discomfort of this agent. And by the way, many of those modules have corresponding subsystems in the brain. The cost module is in the basal ganglia, the world model, the prefrontal cortex. Short-term memory would be the hippocampus. The actor could be the prefrontal cortex, and of course, the perception system is the back of the brain, where all the perception is analysis of sensors is performed. So the way this system operates is that it perceives the state of the world, combines that with its sort of previous idea of the state of the world that may be stored in a memory, and then uses the world model to predict what would happen if the world just evolves, or what would happen as a consequence of actions that the agent would take, which is inside of this yellow actor module. So the actor module proposes a sequence of actions. The world model simulates the worlds and figures out what's going to happen as a consequence of those actions. And then a cost is computed. And then what's going to happen is the system is going to optimize the sequence of actions so as to minimize the world model. So what I should say is that whenever you see an arrow here going one way, you also have gradients going backwards. So I'm assuming that all of those modules are differentiable, and we can do this inference of the sequence of actions by backpropagating gradients so as to minimize the cost. So this is not minimizing with respect to parameters, which would be for learning. This is minimizing with respect to latent variables, and this is taking place at inference time. So there's really 2 ways to use that system. It's akin to system 1, which I call mode 1 here, where basically it's very reactive. So you observe the state of the world, run it through a perception encoder, which gives you an idea of the state of the world, and then run this directly through a policy network in the actor that just directly produces an action. So there's no need for a world model here. It's just a reactive policy. Then mode 2 is one in which you observe the world and extract a representation of the state of the world, S0, and then you imagine, the system imagines a sequence of actions, from A0 to a large T, and then using its world model imagines the result, the effect of taking those actions. Those predicted states are fed to a cost function, and the entire purpose of the system is basically to figure out a sequence of actions that will minimize the cost according to the prediction. So this world model here that is repeatedly applied at every time step essentially predicts a representation of the state of the world at time t plus 1 from a representation of the world at time t and an imagined proposed action. This idea is very much similar to what people in optimal control call model predictive control. And there's a number of models that have been proposed in the context of deep learning that use this idea for planning trajectory, work by my student Michael Enaf and myself, and Alfredo Conziani at ICLR 2019, a series of work by Danica Hafner, Dreamer V1, V2, etc., and other work from Berkeley and various other places. So the question here is how do we learn this world model, essentially? Maybe skip this. What we're expecting to do is some more complicated version of this, where we have a hierarchical system that extracts through a sequence of encoders, extract more and more abstract representations of the state of the world, and use different levels of world models of predictors to predict the state of the world at different levels of abstraction and make prediction at different time scales. So at a higher level here, for example, if I want to go from New York to Beijing, the first thing I need to do is go to the airport and then catch a plane to Beijing. Okay, so that would be sort of a high-level representation of the plan. The ultimate cost function could represent my distance from Beijing, for example. And then the first action would be go to the airport, and my state would be, am I at the airport? And then the second action would be catch a plane to Beijing. Now, how do I go to the airport from, let's say, my office in New York? Well, the first thing I need to do is go down to the street and catch a taxi and tell it to go to the airport. And then how do I get down on the street? I have to stand up from my chair, go to the exit, open the door, go on the street, etc. And then you can imagine decomposing this task all the way down to the millisecond by millisecond muscle control that you need to do to accomplish this task. So all complex tasks are accomplished hierarchically in this way. And this is a big problem that we don't know how to solve with machine learning today. So this architecture that I'm showing here, no one has built it yet. No one has proved that you can make it work. So I think that's a big challenge, hierarchical planning. The cost function can be composed of two sets of costs modules, and would be modulated by the system to decide what task to accomplish at any one time. So there are two submodules in the cost, some that are sort of intrinsic costs that are hardwired and immutable. And you can imagine that those cost functions will implement safety guardrails to ensure that the system behaves properly and is not dangerous, is not toxic, etc. And so that's a huge advantage of those architectures, which is that you can put costs that are optimized at inference time. And so you can guarantee that those criteria, those objectives will be enforced and will be satisfied by the system's outputs. So this is very different from autoregressive LLMs where there is no way basically to ensure that their output is good and non-toxic and safe. Here, it's possible because it's possible to impose this because that's basically hardwired into the system that it needs to optimize those cost functions. And then there might be other cost functions, perhaps trainable, that model the satisfaction of the task that is being accomplished. And those could be trained. Those are similar to critics that are used in reinforcement learning. I'm assuming that all of those modules are differentiable. So how are we going to build this and train this world model? So again, we're going to do something like in this little example here, kind of capture the dependency in video, perhaps predict a segment of a video, a future segment of video from the present and the past. And if you train a neural net to just predict videos, it doesn't work very well. You get very blurry predictions. This is old work here at the top from 2016, where we attempted to do video prediction. And what you get are blurry prediction because the system cannot predict in advance what is going to happen in the video. So it predicts an average of all outcomes. And that ends up being a blurry prediction. There's a similar scenario here at the bottom where this is a stylized picture from a top-down camera looking at a highway and following the blue car. And the predicted frames from this video prediction system are blurry, again, because the system doesn't know exactly what's going to happen. And so it predicts an average, and that's a bad prediction. So the solution I'm going to propose to basically deal with this issue of multimodality is what's called a joint embedding predictive architecture. And so let me explain a little bit what this is. So we have generative architectures, things like autoencoders, variational autoencoders, maxed autoencoders, or the type of large language models I was talking about earlier. And there, what you do is you have an observed variable X, an encoder, a predictor, or a decoder that produces a prediction for the variable you want to predict, Y, and then you measure the divergence of some kind, some distance between the predicted Y and the observed Y. And there's a flaw with this, and the flaw is that the systems have to predict every single details about Y. So this is not too much of a problem when you're predicting words, because you can represent a distribution over words using a softmax, a long vector of probabilities of numbers between 0 and 1 that are normalized. So it's easy when Y is a discrete variable. But when Y is a continuous variable, like a video frame, for example, or a set of video frames, predicting all the details in that video frame is essentially impossible. And most of the details are not even useful to capture. So for this, I propose the architecture on the right, which is called a joint embedding architecture, or in this case, joint embedding predictive architecture. And basically, both X and Y are fed through encoders. And the prediction takes place not in the input space, but in representation space, so that there's a predictor network that tries to predict the representation of Y, Sy, from the representation of X, Sx. A simple form of this joint embedding architecture is something that I proposed many years ago in the early 90s called Siamese network. And those kind of architectures have become somewhat popular over the last few years for self-supervised learning in the context of images. So there are basically no method today, no generative architectures today that work properly to learn features for vision. With one exception, which is a maxed autoencoder from my colleagues at FAIR, including Kai-Ming He. But it doesn't work very well in the sense that the features that are produced are not very good. You need to fine-tune the system to get good results. So if you want features that are good without fine-tuning, the generative methods are really not good. You need to use the joint embedding architectures. So there's a number of methods like Perl and Moko, SimClear, Barlow Twins, and VCREG that essentially use this joint embedding architecture, and they do work very well for self-supervised learning and produce extremely good features. Another method that is not listed here is Dino, which is a method by my colleague at FAIR in Paris. A slightly more sophisticated version includes a predictor that tries to predict the representation of Y from that of X, as opposed to just trying to make them equal. but that would be deterministic prediction. On the right is a version of that system in which the predictor takes as input a latent variable, and that latent variable can be used to parameterize a set of possible predictions of SY and basically make non-deterministic predictions. So you would have a system of this type where if you want to use this architecture to build a world model, the predictor would take two variables, a set of latent variables that represent everything you don't know about the world, all the unobserved variables that represent the state of the world that would allow you to predict what's going to happen next. And then another set of variables that would represent an action you might take, right? So from an observation of the state of the world X, you extract a representation of it, then given an action, and through maybe sampling a set of latent variable, you can make one prediction about the representation of the state of Y, and that Y variable can be run through an encoder. So the next question is, how do we train this system? And that system might include other criteria represented at the top right, like C of S, that may represent constraints that we want the system to satisfy, or cost functions that indicate what type of information we want the system to learn to extract. So before I talk about how we train this, I have to talk a little bit about what's called energy-based models, which is the framework through which we can understand this, because we can't understand those systems through the traditional methods of probabilistic modeling, unfortunately. So what is an energy-based model? Energy-based model is a function, an energy function, that captures the dependency between, let's say, two sets of variable X and Y. And the way it does this is by putting a scalar output, where that scalar output is small, takes low values when X and Y are compatible with each other. So for example, Y is a good continuation for the video clip X. And then it takes higher values outside of whenever Y is not compatible with X. So it's symbolized here in this the diagram on the right, where let's say X and Y are scalar variables, and the set of data points that you've observed are those black dots. So you want the energy function, of course, which is going to be parameterized through a neural net and trained. You want this energy function to take low values around the data points, and then higher values outside. And so basically, you can think of this as an implicit function that represents the dependency between X and Y. Through learning, it's really easy to train this energy function to give low energy for the data points you train it on, but it's harder to figure out how to make sure that the energy is higher outside of the training samples. So there are two classes of methods to do so. One is called contrastive methods, and it consists in generating contrastive points, those green flashing dots here, outside of the manifold of data, and then pushing their energy up, right? So you simultaneously push the energy down of the data points that you have, and then you generate contrastive data points, which must be hallucinated if you want. You push their energy up. And so by pushing down and pushing up on the right place, the energy surface will take the right shape. But my preference goes to something called regularized methods, and they work by essentially imposing a regularizer on the energy function so that the volume of space that can take low energy is limited or minimized. So whenever you push down on the energy of some region, the other regions have to go up because there is only a limited volume that can take low energy. So that's those two categories. I think there is a major limitation with contrastive methods, which is that as the space of Y increases in dimension, the number of contrastive points you need to generate for the energy function to take the right shape grows exponentially with the dimension. And I think that's a flaw. Whereas regularized methods tend to be more efficient by basically minimizing the volume of space that can take low energy. So how we so basically, I'm asking you to accept four things. The first thing is to abandon generative models. Okay, this is not very popular at the moment because generative models are all the rage. Everybody is talking about them. What I'm saying is that if you want to have a system that can learn world models. It cannot do this by just generating, being trained to produce video frames, for example, because it's too complicated to make predictions in high-dimensional continuous spaces. So we have to use those joint embedding architectures, which means we have to abandon the idea that we're going to have generative models. For text, it's fine, but not for video. We have to abandon the idea of using probabilistic modeling and use those energy-based framework. The reason being that you cannot, if you're going to run Y through an encoder, you cannot invert this encoder function to produce a conditional probability P of Y given X. This is not possible in this context. You have to abandon the idea that you're going to model a distribution. You're just going to compute this energy function, which is a proxy, a simpler proxy for something like a distribution. I'm also telling you to abandon contrastive methods in favor of those regularized methods. And of course, for many years now, I've said that if reinforcement learning should be minimized, we should minimize the use of reinforcement learning because it's extremely inefficient. So basically use planning whenever we can and only use reinforcement learning where we have no choice. So what are those regularized methods for joint embedding? And this is really kind of the core of the talk, if you want, the interesting part. Okay, so here's the problem. We're going to have a collapse issue, which is that if we just train one of those joint embedding predictive architecture to minimize the prediction error, which is the error you make of predicting the representation of Y from the representation of X, it's not going to work. The system is basically going to collapse because it's going to ignore X and Y, produce SX and XY vectors that are constant, so that the prediction error is 0. And that model is not going to capture the dependency between X and Y because it's going to give you 0 energy for everything, right? You will have succeeded in making the energy low on your training samples, but the energy will be 0 everywhere. So you have to prevent this collapse from happening. And the technique that I'm proposing here is to essentially have some measure of the information content of SX and the information content of SY and maximize them. Okay, so find a way of maximizing the information content of both SX and XY, and that will prevent this collapse. And in fact, this has the regularization effect I was telling you earlier, basically minimizing the volume of space that can take low energy. If you have a latent variable for the predictor, you also need to regularize the information content of that latent variable, but there you need to minimize the information content. If you have a latent variable that is too informative, you're also going to have a collapsed model that predicts that has 0 energy for any pair XY. So how are we going to maximize the information content of SX and SY? So a simple way in which those systems can collapse is by making SX and SY constant. You can prevent this from happening by having a cost function at learning time that basically guarantees that the standard deviation of all the components of SX is above a certain threshold, in this case 1. So this is a hinge loss that pushes the standard deviation of the every component of S to be larger than 1. Okay, so the system cannot put just constant outputs, and this is computed over a batch, if you want, of a few samples. We do the same thing for both SX and SY. So this is called variance regularization, and there's a number of papers here at the bottom that have been using this method. Coming out of my group from Meta, Barlow Twins, which was the first version of this, VCREG, which is an improved version, VCREG-L for image segmentation. And this is similar to a work by Yi Ma at Berkeley. He's actually now in Hong Kong for some time, co-authored with Harry Shum, called NCR squared, which has a very similar idea. So that is not sufficient to prevent the system from collapsing, because the system could choose to make all the components of SX equal or very correlated. And so what you have to do as well is basically minimize the off-diagonal terms of the covariance matrix of SX. So you take pairs of coordinates, measure their covariance, and for 2 different coordinates, you try to minimize the covariance term. So basically, the cost function is the square of the covariance term for every pair variables. So that will decorrelate the variables, and that's still not sufficient. And so what we do is play a trick here. We run SX through an expander module that produces a larger vector Vx. And then we apply the variance covariance criterion to this larger vector Vx. And this actually has the effect, and we have some papers on this. This will have the effect of making the components of Sx more independent with each other, at least pairwise independent. So this method is called VICREG, and that means variance, invariance, covariance regularization. So variance is this criterion, covariance is that criterion, and then invariance is this prediction criterion. VICREG. We're really happy with that method. It works really well. So we can train one of those joint embedding architectures with pairs of images, which are distorted versions of each other. So it's the same model as I was talking about earlier, where you take an image and you corrupt it. And here, in this case, you transform it in some ways. You train this joint embedding architecture using VICREG, and then you chop off the expander, or the projector in this case, use the representation produced by the system as input to a linear classifier that you train supervised and measure the performance. And this works really well. You can get something like in the mid 70% correct on ImageNet with a very simple architecture. We're using convolutional net architectures. And something like ConvNext and things like that. You can now apply the features to other tasks than ImageNet. This is pre-trained on distorted versions of ImageNet. And it works pretty well, including for segmentation, but not perfectly. So you can improve that system by a very simple predictor that tries to match the location of features into images. This is called VICREG L for local. And that works really well for segmentation. So that system really produces fantastic features for segmentation. I should say that another method that is also a joint embedding architecture by our colleagues at FAIR Paris called Dino, and Dino V2 also produces excellent features for segmentation. And it's very similar in many ways. The collapse prevention is different, and the representations are quantized, but in many ways it's a very similar idea. Let me skip ahead a little bit. So this is a more recent work called ImageJEPA. And so this is one of those joint embedding predictive architectures. And there it's purely based on masking. So we're not doing data augmentation. We're just taking an image, running it through an encoder, producing a representation. And in this case, the encoder is a transformer. So we get a complete representation of the image through the transformer. And then we run a partially masked version of the image through the same transformer. So those two share the weights. So this system produces, weaker partial features. And then we train a predictor to predict the representations produced from the full image from the representations obtained with the partial image. So again, ImageJEPA. This is a recent paper by Mido Asran from FAIR in Montreal in collaboration with some of us. And this works amazingly well. It produces really good features. It's very fast, and it doesn't require any data augmentation, which is a huge advantage. It works much better than, for example, masked autoencoder, which is a generative architecture. And it really doesn't require any data augmentation. It can reach something like 81% on ImageNet, which is similar to what other methods can reach using data augmentation. So this is without using data augmentation, purely using masking, which is pretty amazing. And of course, it works really well for transfer tasks and things like that. So, okay, so how are we going to use this? I'm coming to the end of my talk here. We're going to use this to build those JEPA architecture, to build hierarchical world models that will be integrated in this full architecture that will allow systems to plan. And what I'm talking about here is the future, because we haven't built this completely. We have some demos of some subsets, but no real complete system yet. So we can use one of the JEPA architectures to extract low-level representations of the input and make predictions at short term with lots of details. Or what we can do is run through another encoder that is going to extract a higher level abstract representation and make predictions that are longer term, so further in the future. The low level may involve actions that are real actions in the real world, and the higher level will involve latent variables that may represent high level actions that do not correspond to real actions. And we could use this system, this architecture, in the context of hierarchical planning that I was describing at the beginning of the talk. So we built some versions of this type of hierarchical architecture for video prediction. We don't think we have a perfect recipe yet, but we have something that seems to learn pretty good features from video. So it basically takes 2 frames from a video, runs them through encoders, and then has some predictor that tries to predict the representation of the lower frame from the representation of the first frame, but it does this hierarchically, and simultaneously the same encoder is used to and train from images using the VCRAG criterion I was talking about earlier. Both of them use VCRAG regularization at every level. So I'm not going to describe the details of this architecture, but basically it's a large convolutional net, and the predictors have a particular structure that basically force the representations to follow some sort of geometric warping, and the warp vector fields are predicted from top to bottom, and basically that system spontaneously, using self-supervised learning, learns the distortion between 2 successive frames in a video and learns to extract representation that represent all the information. If you train that simultaneously with a sort of global image recognition criterion, you get systems in the end that can estimate flow, optical flow, but also can extract representations that can be used for object recognition and segmentation. And we have really good results, which I'm not going to bore you with, but of a system that can simultaneously perform a good flow estimation, object recognition, and object segmentation, and object tracking as well, using completely self-supervised learning. So I'm going to the end. So if we are successful in making systems of this type that are completely general, we're going to be able to integrate them into systems that can predict what's going to happen as a consequence of actions or latent variables, and then use those systems to make to do planning. And to some extent, planning through energy minimization can be seen as a very general framework for reasoning. Reasoning can always be sort of formulated in terms of minimizing some energy function, and so this is much more sort of qualitatively more powerful than autoregressive generation. So steps towards AI systems: self-supervised learning, handling uncertainty in prediction using those JPA architectures and this framework, learning world models from observation using SSL, and reasoning and planning by using energy minimization with respect to action variables. And so this is a kind of reasoning that does not involve any symbols or any logic. It's basically just continuous optimization with vectors. Okay, is there a chance that this kind of architecture will lead us towards human-level intelligence? Perhaps. We don't know yet because we haven't built it, and it's probably going to take quite a long time before we make it work completely. So it's not going to happen tomorrow, but there's good hope that this will take us a little closer, perhaps, to human-level intelligence, where systems can reason and plan. An interesting tidbit about this is that those systems will necessarily have emotions, because the ability to predict an outcome, whether an outcome is going to be good or bad, which is basically implemented by the cost module, is kind of very similar to emotions in animals, right? Fear is caused by an anticipation of a potentially negative result, and elation is produced by the prediction of a very positive result and things like that, right? So systems that are driven by objectives like this, I actually call this objective-driven AI, will have things like emotion, they will have drives, they will be controllable because we can set them, we can set goals for them by through those cost functions, so much more controllable than autoregressive models. And by designing those cost functions appropriately, we can make sure that those systems won't want to take over the world and, on the contrary, be subservient to humans and safe. And I'm going to stop here and thank you very much for your attention.
Well, thank you very much, Jan, for the very insightful talk.